morning, students. In a previous lecture, we have gone through the terms, components and phases of a system. Now next one is the degrees of freedom. So how we can define the degrees of freedom? There are two ways to define the degrees of freedom. First one is, it is the minimum number of independent variables such as temperature, pressure and concentration of components in various phases which must be varied independently in order to completely describe the given state of a system at equilibrium. So what we can say, degrees of freedom is what? Minimum number of variables out of temperature, pressure and concentration, which can be varied independently in order to completely describe the state of a given system at equilibrium. That will be known as degrees of freedom of the system. In the same way, we can explain it as the number of variables such as temperature, pressure and concentration which can be varied independently without disturbing the number of phases present in equilibrium. So in summarized form, what we can say, degrees of freedom is what? It is the minimum number of independent variables out of temperature, pressure and concentration which we can vary independently so that we can completely describe the given state of system at equilibrium. So it will be more clear with the examples in the coming slides. For example, we are having a water system in which the three phases are in equilibrium: ice, water and water vapor. So in this case, phases are three and the component is one. Component is only water, so component is one. So using the phase rule, we will see the degrees of freedom are equal to 0. So in case of water system, when all the three phases will be in equilibrium, the degrees of freedom will be 0. It means out of temperature, pressure, a composition is already fixed in case of water system. So out of variables, temperature and pressure, we can't vary any one of these so that we can completely describe the given state of the system. When all the three phases are in equilibrium, we can't vary temperature and pressure. Any one of these we can't vary, only at one particular temperature and one particular pressure, all the three phases will exist in equilibrium simultaneously. So for the coexistence of three phases simultaneously in equilibrium, there must be only one temperature and pressure. So there is no degree of freedom, there is no variation possible in any one of these. So system is having no degree of freedom. Now in the same case, when the two phases are in equilibrium, water and water vapor, in that case phases are 2 and component is 1, so degrees of freedom comes out to be 1. So when two phases are in equilibrium in a one component system, the system will be univariant. Out of temperature and pressure, only one can be varied independently. The value of other will depend automatically on the value of other variable. So in this case, we can independently vary only one variable. The system is univariant. So for one component system, when two phases are in equilibrium, only one variable can be varied independently without disturbing the number of phases present in equilibrium. Now, for a one component system, when there is only one phase, for example gaseous phase, the P is equal to 1 and component is already equal to 1, as we are talking about the one component system. So degrees of freedom in this case comes out to be 2. So in case of a one component system, for a single phase, the degrees of freedom are 2. So two variables can be independently varied. So temperature and pressure both can be varied for a single phase in case of a one component system. These all things will be more clear when we will study the phase diagram of one component systems like water system, sulfur system. These all things will be more clear. So in case of one component system, when all the three phases are together, degrees of freedom are 0. When only two phases are in equilibrium, degrees of freedom is 1. And when there is only one phase, single phase, in that case degrees of freedom are 2. Now, next is the concept of equilibrium. A system is said to be in the state of equilibrium if the properties like temperature, pressure, composition of various phases, they are do not undergoing any change with the time. They are remaining same. So different types of equilibrium are there: true equilibrium and metastable equilibrium. First one, what do we mean by true equilibrium? A system is said to be in a state of true equilibrium if the same state can be achieved by approach from either direction. We can get the equilibrium for forward direction as well as from the backward direction. So this is the state of true. So ice and water, they are in equilibrium at temperature 273 Kelvin and at pressure of 1 atmosphere. This equilibrium can be attained from either side, either by melting of ice or by freezing of water. So it is a true equilibrium. Now, what do we mean by metastable equilibrium? A system is said to be in a state of metastable equilibrium if the same state can be approached only from one direction, and that too by very careful change of conditions. Very slow change of the condition will lead to the metastable equilibrium. For example, we want to get the state of water at -2 degrees Celsius. So very carefully see, below 0 degrees Celsius, we are getting the stage of water at -2 degrees Celsius. So this is a supercooled water. So it can be obtained only by careful cooling of water without appearance of ice, but it is not possible to obtain by melting of ice. We can only get the stage only by careful cooling of water, not by melting of ice. So such a state will be maintained only if no shock, no stirring or seeding taking place. If there is no disturbance is taking place in the system, very carefully we are cooling the water so that we are getting it at a stage of at a temperature of -2 degrees Celsius. If little disturbance will be there, solidification will start and the temperature will rise to the 0 degrees Celsius. As we will disturb the system, immediately this metastable system will move to the true system. This supercooled water will quickly solidify and temperature will rise to 0 degree Celsius. So this is a state of metastable equilibrium. Now, what are the conditions for various phase equilibrium? So there are three equilibrium when existing simultaneously. The different phases are in equilibrium. First one is the thermal equilibrium. In this state, when we talk about the system in thermal equilibrium, the temperature of all the phases of the system must be same. Otherwise, heat will flow from one phase of the system to another, or you can say one part of the system to the another part of the system. So the condition of thermal equilibrium of the system is temperature of different phases is same. Second thing is the mechanical equilibrium. According to this, all the phases of the system will have the same pressure. There will be no work done by one phase of the system over another phase of the system. So in this case, pressure of each phase will be same. Third thing is the chemical equilibrium. In this state of equilibrium, the chemical potential of a component will be same in all the phases. So for a component I distributed in phases A, B, C and so on, a multi-phase system at equilibrium, then what we will see, the chemical potential of component I is same in all the phases. So it follows that for a multi-phase system at equilibrium, the chemical potential of a component I is same in all the phases. When all these three equilibria are existing simultaneously, the system is said to be in equilibrium. Now, what do we mean by chemical potential? We very well know for a solution containing a number of components, the chemical potential of any component is the increase or decrease in the free energy taking place when we are adding 1 mole of that component to the system and keeping amount of all other components constant at a constant temperature and pressure. So chemical potential of a component is what? Which is the increase or decrease in the free energy of the system taking place when we are adding or subtracting 1 mole of that component from the system. The condition is that the composition or amount of other component is constant and temperature and pressure are also constant. Now, since a system consisting a number of phases in equilibrium constitutes a closed system, a number of phases in a heterogeneous system, they are in equilibrium, that constitute a closed system. So, the total free energy of the system should remain same at constant temperature and pressure. So, the free energy change at constant temperature and pressure will be equal to 0 for such a system. So, how we come to the conclusion? Suppose we are having a number of components are distributed between two phases A and B. Suppose at constant temperature and pressure, a small amount of component 1 is transferred from phase A to phase B. If mu1A and mu1B are the chemical potential of component 1 in phase A and phase B, then the decrease in free energy of component 1 in phase A, that will be equal to mu1A into del N1, where del N1 is the number of change in number of moles of component 1, the amount of component 1 which has been transferred. Similarly, increase in free energy of component 1 in phase B will be equal to chemical potential of component 1 in phase B into amount of component 1 transferred. So, total free energy change will be equal to minus mu1A del N1 plus mu1B del N1, that will be equal to 0. As for a number of phases in equilibrium, a heterogeneous system is having free energy change equal to 0. So, what we are getting here, the result is the chemical potential of a component should be same in all the phases. That is the result we have already discussed for the chemical equilibrium, that why for chemical equilibrium the chemical potential of a component is same in all the phases. So, in terms of chemical potential, we have already discussed that chemical potential of a component should be same. Now, chemical potential is what? It is a molar free energy. So, we can also say the molar free energy of a component will remain same in all the phases when the system is in equilibrium. Next one is the derivation of Gibbs phase rule. It's a very important topic. Now, J.W. Gibbs put forward a relationship that we have already discussed, that is the relation between the number of phases, the number of components and the number of degrees of freedom, which must be specified in order to define a heterogeneous system. It is known as phase rule. A relation between these parameters which is defining a heterogeneous system in equilibrium is known as phase rule. Mathematically, we can write it as this, and this rule is applicable only at the state of equilibrium. When different phases are in equilibrium, this rule is applicable. Now, we will derive this rule. So, for this we are assuming a heterogeneous system having P phases and C components. So, there are P phases and C components. Now, the degree of freedom will be given as total number of variables defining the system minus number of relation between various variables at equilibrium. The total degrees of freedom of the system will be equal to total number of variables defining the system minus number of relations between various variables at equilibrium. So, how we are getting this? First one, various variables are temperature, pressure and composition. Now, for the system to be in equilibrium, temperature and pressure of different phases are same. For a component, temperature and pressure of different phases are same. So, at equilibrium, we can say each phase will have same temperature. So, the one variable is temperature and second variable is pressure. Pressure of each phase is same. So, second variable is pressure. So, two variables are there, temperature and pressure. Now, third we come to the composition. A single phase containing C components can be defined by C minus 1 concentration terms. How we can say this? For example, we are having a single phase in which we are having C components. Now, to define this, if we know the concentration of the C minus 1 components, the concentration of component C will be equal to total minus concentration of the C minus 1 components. For example, if we are expressing the concentration in terms of mole fraction, and if we know the mole fraction of component 1, 2, 3 and up to C minus 1 components in phase 1. In phase 1, the concentration of the component C minus 1 we know. Then we can easily find out the mole fraction of component C in phase 1. So, a single phase containing C component can be defined by C minus 1 concentration term. If we know the C minus 1 concentration term, we can define the concentration of all the components in a given phase. Now, total number of phases are P. For a single phase, we require C minus 1 concentration terms to define. For P phases, multiplying it by P. Thus, all the P phases will have total composition variable to define the system, that is P into C minus 1. Repeating again, for a single phase, C minus 1 concentration terms are required to define the system. Now for P number of phases, we will multiply it by P. So total number of composition variables for the P phases will be P into C minus 1. So adding all the variables, we get the total number of variables defining the given system, that is P into C minus 1, which are the composition variables, plus one pressure variable and one is a temperature variable. So total number of variables are P into C minus 1 plus 2. Now next we move to find out the number of relationship between the variables at equilibrium. For that, we will find out the number of equilibria required for the given system to be in phase equilibrium. We very well know the conditions are temperature of different phases are same, pressure of different phases are same, and third one was the chemical potential of each component is same in all the phases. So from here we are getting one restriction which we will subtract from total number of variables. So for a multi-phase system at equilibrium, the chemical potential of a component is same in all the phases. Now for P phases, the number of such relation for each component will be equal to P minus 1. For example, we are talking about ith component and total number of phases are P. So total number of such equations for P phases will be equal to P minus 1. So for a single component and P phases, total number of such equations are P minus 1. Now for C components, total such equations will be C into P minus 1. So total number of relationship at equilibrium is equal to C into P minus 1. Repeating again, for a single component, for a P number of phases, we are having total P minus 1 such equations. Now for total number of C components, C into P minus 1 such equations. So number of relationship at equilibrium for C components and P phases is equal to C into P minus 1. Now we very well know the total number of degrees of freedom are calculated as total number of independent variables defining the system minus number of such relationships at equilibrium. So what we are doing here, we have calculated the total number of variables which is equal to P into C minus 1 plus 2 minus total number of relationship at equilibrium. So finally we are getting the expression for the Gibbs phase rule, which is giving the total number of degrees of freedom is equal to total number of components minus total number of phases plus 2. So this is all about the derivation of Gibbs phase rule. Next topic we will continue in the next lecture.